Hello everyone, welcome to my PhD defense presentation. My name is DiWu. I'm working in the Department of ICT and Natural Science, as well as the Department of Computer Science in NTNU. The topic of my PhD thesis is Computational Risk Analysis for Digitizing Sustainable Urban Water Supply Systems. Because this is an interdisciplinary research, so my supervisors are coming from different backgrounds, including Dr. Hao Wang and Kirsten Bark from the Department of Computer Science, and also Professor Razak Saidu from the Department of Civil Engineering in NTNU. This work is based on the collaboration between the Sustainable Digital Transformation Group and the Smart Water Lab. I am going to introduce several sections about my PhD work, including the introduction to explain the context and motivations of this research, as well as the objectives. And also I'm going to introduce the design for digitized urban water supply system framework, and also the computational risk analysis in the urban water supply systems. All of those content will be introduced through my published papers. In the end, I'm going to conclude and suggest some future works. Let's start with the introduction about this research. We are now in the global process of urbanization. According to the numbers from the World Bank, in the 1960s, only 34% of the population are living in the cities. And this number has increased to 56% in 2019, and it is projected to be over 66% by 2050. People are coming to the cities in order to look for a better living conditions. But this fast growth of population in the cities have also brought a lot of new problems, including the food, the environment, as well as the services of the public sectors. So in order to guide the cities for new development strategies, in 2015, the United Nations has published 17 different sustainable development goals. This has been well accepted by most of the cities in the world, and their aim is by 2030 to build a more sustainable city in the world. Water is a very important topic and a very important factor to support the city life. So actually in the SDG Goal 6, they have listed clean water and sanitation. So in order to help people to get clean and enough water in their cities. So in order to advocate to use the current ICT technologies and tools to support those type of development. And in 2016, the United Nations initiated the United for Smart Sustainable Cities, U4SSC collaboration, in order to encourage more cities in the world to join this collaboration and to make our city life become better. And in 2019, our city in Ålesund in Norway has been also accepted by this collaboration, and we have built the UN lab in Ålesund. We have developed a series of KPI index according to the Sustainable Development Goals, including the water sanitation. We can see that we have a lot of deficits still. We have a room to improve in the water. However, our quality of the water in Ålesund has already get a green label, which is high in the Sustainable Development Goals. So my work is related with this collaboration. In this context, my work has been initiated by supported by the project from the research console from Norway, and both by smart planning of the city and also the smart water supply. So the objective of these theses is to digitize the obsolete urban water supply system in the cities with feasible and efficient ICT knowledge and technologies to realize the systematic and sustainable risk detection and control. So we have divided these thesis research objective into four research questions, including research question 1, what effect do the sustainable development goals have on the new generation of urban water supply system in the digitized environment, including 2 sub-questions, what perspectives should be considered when designing an architecture for digitized urban water supply system with the clean water goals and the state-of-art supporting technologies. And the second sub-question is that what is the working mechanism from the overall objectives to concrete computable urban water supply system indicators concerning the data, information, and knowledge domains. As you may know, that the urban water supply system is a very old infrastructure in most of the cities. So the urgent need is to upgrade those supply systems in order to meet the requirements of digitization and also trying to provide us better knowledge and monitoring and do the risk control for those old systems. The second research question is what are the different detailed indicators' contributions to their priorities toward computational risk evaluation in the urban water supply system with respect to different objectives and constraints. We have settled up, for instance, the big goals like sustainable development goals, and also we have to meet the requirements from the local regulations like the national standard, and we also have some local development goals for the water supply system. So what kind of data it can collect and help us to control the risk for the water in the supply system? It's a big challenge. So this has been divided into 2 further research questions. What are the joint profiles for urban water supply system sufficiency, safety, and sustainability objectives, and their effective indicators in the risk identification? What factors are related with the risk in the water supply? And the second question is what is an opposite risk representation synthesizing urban water supply system objectives, related indicators, and various forms of constraints. Because we have some geographical constraints and the different types of water sources, and so how could these be supporting our risk identification, and how these will be affect the control of our risk? And the third research question is to what extent the computational risk in the urban water supply system can be analyzed and predicted to provide early warning for decision-making support. The water quality is a very important topic and is highly related with public health. And so as long as we can provide some warnings in order to avoid the risk in the water quality and also the quantity will be helpful in the public service. So this is also a very important research topic in this thesis. And so this has been divided into 4 different sub-questions. What scheme can facilitate to analysis of computational risk in the urban water supply system from a smart data-driven perspective? From the data we collected, what knowledge it can contribute. And the second question is, based on the feasible data collections, what methods can be applied to predict the water supply risk considering space, time, frequency domains? And the third question is there a renaissance, in fact, among risk evaluations of urban water supply system from distinct geographical environment? So maybe based on different data collections from different cities based on different geographical environment, and what new knowledge can we find in order to identify and predict the risk in the water supply systems? And the fourth question is, what support can be taken from the relationship analysis within the risk in the urban water supply system for the prediction requirements? And in addition, this is a very practical work. So the fourth research question is more for application. So when we applied our methods and technology, what challenges and technical issues are there during the process of application, development, and deployment proposed methods to practical urban water supply system? We have also done some work in this field as well. This thesis has been included some of my publications during my PhD work. I have listed 6 different publications. Well, it's all have done by me and my supervisors, and I was the leading author for all of those 6 papers, including 2 journal papers, and one already get to the citations for over 21. And also there was 1 paper from the high-level international conference on the information and knowledge management in 2019, and also some other papers are in the related area in the conferences. This is the mapping between my research questions and to my research papers. There are 4 different research questions and 6 different papers. I'm going to explain the details from there. So the second part, I'm going to introduce about the digitized urban water supply system framework design. This has been published in my first. In the first research paper, we discussed the design of digitized urban water supply system framework. The aim of the urban water supply system is to bring safe and sufficient water to the end consumers from different water sources. So from this figure, we can see that a common urban water supply system has 3 sectors, including water sources. There are different types, including common one, including lakes, dam, under well, and also in some extreme cases, they have the water from the ocean. And those water from the sources will be brought to the water treatment plant. And during the process of treatment, and the water will be brought to the different end users, for instance, factories, residential communities, hospitals, and schools. So during this process, we need to monitor and to observe what happened and whether the safety are okay, whether the water is sufficient. So based on those objectives, according to the cyber physical system architecture, we have designed a general architecture for the urban water supply system. And these has 5 different hierarchical levels, including the end level connection, and also the conversion, and also cyber, that we have collected the data from different places from a network, and also cognition, and the top level as configuration. The data has been flow from this direction, from the basic sensors to edge or cloud, and from there we can get some functions of those data, and those data will be transferred for management perspective, and then at the top level, and it will be supported for the water strategy and policy. And when the policy has been made, and then we'll transfer the knowledge to the objective, and then to the index breakdown. And with the index, we can make new sensors, and we can design new sensors and make new data collection strategies, and at the end to make an optimal deployment. So this is the mechanism and architecture for the digitized urban water supply system. And during this process, and the information, data, and knowledge domain has been interacted between each other. The data we use in this architecture, including the real-time data that we collected from the sensors, all types, and historical data, maybe from the storage, and processing data, because the data, the raw data has been gathered in the information processing perspective, and also these will be processed data, and also these will be stored and also for further use. And at the same time, this information processing process will be taken the knowledge from the domain, including the sensor knowledge, the data knowledge, and the cyber physical system knowledge, and also water knowledge, because the domain expert from the water supply, they also have their own experience and their own models, and to evaluate and to monitor and to give different perspectives to the processing of the information. So those results data will be all stored. And so during this process, from the three domains, data, information, and knowledge, they start to interact. And fortunately is that during this process, especially from the data, we can dig out new knowledge. From this work, we also developed a series of performance evaluation index for the digitized urban water supply system, including three basic categories: the quantity index, the quality index, and sustainability index, which corresponds to different performance requirements in the water supply system. And here we have given the detailed definition of those index and the calculation formulas. And we are trying to implement this idea to our local city, Ålesund. This is the map of our local city. And here you can find the Brustadvanet. It's the main water source for our city. It's quite a big lake. And we are planning to deploy integrated sensor stations in this water source. And also, in order to avoid some risk, we also have some backup plan for the water source. Here in Ålesund, we have two smaller lakes to serve as the backup for the water source. So here are the planning integrated sensor stations. And also we have in the city, there are some water reservoirs which serves as the temporary storage for the water. So here are their locations. And we also build the data center, which is here. This is the location of our school. And from here, we can collect the data from those sensor stations and process them and provide a certain level of services for the local people with respect to the water supply, including the quality and the quantity with the supply system. And here is the treatment plant in the city. Next, we are going to talk about how do we model and how do we predict the risk in the urban water supply system. And this is tightly related with our data collection process. So this part of the work, we are going to use 5 different papers to introduce. After we build the digitized urban water supply framework. In the second paper, we are going to model the water quality related risk in the supply system. And here in this paper, we have described our findings in the water quality in a kind of three-order tensor. And here we have used the three-order tensor to describe the data we collected, including the locations, which can be different cities, and also the time domain, which can be weeks, can be minutes, can be years, and also the quality parameters. In Norway, the water quality is controlled by a series of water quality index. And those index, for instance, there are physical index like temperature, pH values, and also chemical index like the alkalinity index, and also a series of bacteria index like coliform, E. coli, and stuff. So in this paper, we are trying to predict the water quality parameters. And here, based on this model, we have used a simple random forest to predict the bacteria, because normally in practice, the bacteria is the direct threat to the human health in the public water supply system. And in Europe, the water can be directly drank from the taps, so the bacteria is seriously controlled in Norway. So here we use random forest to predict the value of the bacteria in this data that we collected from the Oslo commune, including we have listed 4 different types of bacteria. This is based on the historical data collected from 2009 and 2015, including coliform, E. coli, intestinal, and also Clostridium perfringens. So those are we use a simple prediction for this water quality index. But however, we find that the peak values and also the prediction results was not very satisfactory. So that's why in order to better predict the water quality index, we have developed our work into the 3rd research paper. And first we have designed a framework to analyze the data. From data collection, we have collected the data from environmental, physical, chemical, and biological indicators. And because they are raw data, and based on the sample testing and result paradigm, which makes the raw data is full of errors and missing values and these problems. And so we need a full process to pre-process the data. We use cleaning, synchronization, and normalization to help. And we also use the correlation analysis to help to find the features, important features among those indicators with respect to the water quality. And we separate the data set we collected into training and testing. And we are trying to build a model that can predict the water quality indices. In this paper, we have developed 2 different algorithms to predict the results. The first one is adaptive learning rate neural network. Because the water quality index if you see the evolution, it's fully non-linear. So the neural network is the first choice. However, because of the because the data size we can collect are very limited, although it looks like from 2009 to 2015, but based on the traditional way of how to monitor the quality index in the cities, they are trying to take the sample every week. So every week we just have one set of data. So for 7 years, we only have over 350 groups of valid data. So these way, although we have improved the learning rate step by step, and the prediction results was not very satisfactory. So in addition, we have developed another algorithm which is based on random forest. But this is, we find that the low risk water quality, especially with respect to the biological indicators, the bacteria, and we find the low risk are not very, the prediction accuracy was not very important for us. We want more focus on the high risk of the water quality index. So here we use a two-step in order to improve the prediction quality. So first, in the first step, we use isolation forest to separate the low risk and the high risk water quality index. This is based on the different choices over the depth of the tree. And then the second, based on the second step, based on the low risk and high risk, we use different models to predict their results. So in this case, we have improved the prediction accuracy. So here is the results. We have evaluated our result by the RMSE and MAE, and for our data sets, both from Oslo and Bergen. Those are the two big cities in Norway. And so here we have found that in order to, our aim is that from the easily collected data, physical and chemical data, because they are fast to get the results. We want to use those indicators in order to predict the bacterial data, because the bacterial data usually takes a long time to get the results. Sometimes you need 24 hours to 48 hours to get the results. So here is the results. We can see that by different places, for instance, in Oslo, by different algorithms, we have compared the traditional artificial neural network, the adaptive learning rate, the usually random forest, and the two-step random forest. We can see that the random forest, the two-step isolation and random forest algorithm can greatly improve the accuracy of our results, and as well as the parameter or the indicator interaction. You see, we can collect a series of indicators, physical indicators, chemical indicators, and biological indicators, but the complex interactions between them are difficult to be understood even by the domain experts. So we are trying to use data to understand their relationship. So here we find is that by the traditional correlation analysis on different different bacteria, we can see that the pH values is more useful in Bergen area. But however, in Oslo, we find that the temperature is more sensible with respect to the different bacteria. So here is we can find that the different or easily accessed physical or chemical indicators have different impact for the bacterial index. And so in that case, maybe we can consider to use the physical or chemical index to be the early warning as the water quality for the bacteria. However, we find that between different cities, those indicators are not unified. So this is one of our findings. And this paper has been cited for over 20 times. And I think the contributions can be listed as this is the first efforts to integrate the data-driven technologies with smart water supply system for the water quality control. And this work is essentially a first step toward developing the necessary tools to improve the comprehension of the interactions among those water quality indicators, because the domain experts understand the water quality through those indicators and how they result in the varying levels of different quality indices. And also it takes the advantage of the modern big data technology to solve a traditional water quality control question. These provide the basic risk control and to support the further decision for the urban water supply systems. And so this is our start to try to see how the water quality can be controlled by the data-driven technologies. In order to improve the prediction accuracy with respect to the water quality, in the fourth paper, we are trying to investigate the prediction from the cycle or frequency domain. Here in this paper, we have developed a different framework to analyze the data, including to find the cycles in the water index, quality index, and also about the peak value calculations, and also we are trying to use the raw data to correct our model functions, and in order to calculate the risk in the system. So here we have developed a new algorithm for the water quality frequency domain analysis. And also the other algorithm is trying to predict the water quality index. From this paper, we have used more data that collected from Norway, including 4 different cities, Oslo, Bergen, Ålesund, and Strømmen. And by our analysis with respect to the frequency domain, we have found that among different cities, and we can see in some cities, you can see that the parameters are changing to show a kind of year as a cycle for their evolution. But this is not happening with all the cities. This is we evaluated also because the data quality issues that from the collection process. And from this work, and we are also trying to use the frequency domain to predict the water quality index. And here we have compared our methods, the frequency prediction, and also the neural network and random forest. And here we find that the frequency has shown much lower in the RMSE and for the prediction of the bacteria index, and also the as well as the comparison with different regions with RMSE, and this is the comparison between the peak values, because in the reality the peak values are also the important index we use to evaluate the risk level with respect to the water quality. Further on, we have written another paper that trying to take the advantages for the data collection from different cities and trying to use a collaborative analysis for the computational risk urban water supply system. And in this paper, we have built mathematic models and to evaluate the risk. First, considering about the bacteria, we have considered the bacteria in different cities and the speed of their propagation and the survival ability for this bacteria in order to and also their observed value in order to predict their risk. And also we have defined the model to evaluate their similarity between different cities, and in order to have a general concern over a general overview of the risk level among different cities. And also we have a formula to predict the risk. In this work, we have developed a similarity matrix for the bacteria in the 4 different Norwegian cities. And we can see that there are some, we can see they have some higher correlation, but at the end the correlation was not very obvious. with this work, we also developed the risk map between different cities and between different bacterial levels. And also this is the prediction, and the comparison is based on the scaling issues as well. For instance, the week prediction and the season prediction and year prediction. Also, we considered that if the input as the physical chemical indicators or only bacteria indicators. And also we compare that it's a random prediction, which means that we have split the test and train data into different random manner, or we are doing the time series prediction. And from these results, we can see that with the help of physical and chemical indicators, we can get better prediction accuracy in the performance. And the sixth paper in our thesis is a bit our early stage work. And from this work, we are trying to use also the correlation analysis and to see what kind the interactions between different parameters in the water quality. And also we used the ZIP, zero inflated poison model, and for prediction. And also we tried another zero inflated negative binomial model to predict the water quality index. Here is what we find is that the relationship between the alkalinity and color are a bit higher, and also the conductivity and color is higher. So in that case, we are thinking that some indicators maybe we don't need, if they have very high level correlations, we don't need to deploy those sensors, and we can use them. We can use the findings, and in order to find what kind of sensors do we need the most to predict or is highly related with the bacteria indicator. But from the beginning of this work, we haven't found that they are so close. Also, by the preliminary work in this paper, we have found that there are some interesting phenomena. First is that the cycles of those index, for instance, the pH values and the temperature, they are changing by season. In this paper. This paper, the data source is coming from Oslo Commune. And also we find that the alkalinity is a chemical indicator, and it is this, for instance, when the alkalinity become very flat, and next we can expect a kind of peak value in the bacteria. It happens with E. coli, with E. coli coliform or other types of bacteria. But this is cannot be confirmed by the domain expert. So it's just based on our findings on the data. So this is our findings with respect to the 6 different published papers. I'm very glad for to be involved in this work, and I'm glad to see the progress of this work with my very dear colleagues from the Smart Water Lab. And we have realized, we have implemented, and we have developed and deployed a sensor station in the water source in Ålesund in order to help to digitize our water supply system. And here we have used a kind of boat that had deployed on the lake, and also this can test the water indices more frequently. And currently we have the data for every hour, and they can remotely send to our data center. And this is the location of the sensor station, and this we have also used a weather station to monitor the environment indicators. And this is the core sensor station, which has integrated the pH sensors, the temperature sensors, and alkalinity sensors, and so on. And yeah, so hopefully in the future we can use those data, which has we can collect more data from our findings and to get more knowledge for the water supply system. And to conclude our work, so we have proposed 4 different research questions in the thesis and end up with 6 different research papers. And during the research papers written process, we have also implemented and developed our system and for the digitized water supply system. And the contributions for this thesis is to establish a general architecture for the digitized urban water supply system, and also construct a computational risk model formulation to identify and evaluate the multi-water supply effective indicators, and also build a data-driven analysis schema to for computational dynamic risk evaluation, and applied or proposed architecture and corresponding methods to multiple no-vision urban water supply systems. And there are some limitations which is based on the data collection, and on this part we are trying very hard to improve this. So for future work, I suggested like from 2 different directions. One is the quality evaluation and maintenance for the urban water supply system data collection. So we want to have better quality sensors and more types of sensors in order to provide us better resources for the data analysis and provide better prediction and control of the risk in the system. The other is about federated learning approach in the risk modeling and prediction. This is based on that in the water supply system is very conservative subject, and every cities, they want to keep their own data. So this makes actually the collaborative learning very difficult. So with the current technology in the federated learning approach, and then they can keep their data, but we have a better, we can provide a better service and training and for them. So this is I suggested the 2 future research directions. So thank you very much for your attention.